Okay, so let's continue to study. This very interesting pair of triangles here. Uh, we were actually looking at a uh, rigidly rotating triangle, this blue triangle, and it's rigidly rotating about its side median point x6. And then we actually lit up an inversion circle of a certain radius that I can choose, and at a particular center O that I can choose as well. And what we did was we computed a triangle, a red triangle, whose vertices were inversive images of the original blue vertices with respect to this circle. Okay, and what we mentioned in the previous video was that a very interesting phenomenon occurs here, that regardless of the position of my inversion center, O, the symmedian point of this inversive image, the red family, was stationary. And I'm representing that by x6 to the minus 1. This is not the inversion of the symmedian point with respect to the circle. Rather, it is a symmedian point of this new triangle here. Okay, so these are not the same operation. Obviously, if this x6 here is stopped, the inversion with respect to the circle, it's going to fall somewhere here, is going to be a um, so this could be an interesting thing, right? So I just answered my own question. Is the location of this stationary symmedian the inversion of x6 with respect to the circle? If this were the case, um, if I made the radius of my circle be exactly equal to x6, okay, if the red dot were the inversion of the blue dot, it would have to fall right over this inversion circle, and it's not happening. So x6 to the minus 1, the symmedian of the red family, is stationary, but it is not the inversion of x6 with respect to the circle. Okay, so as I move my center of inversion around, and I continue to gyrate the blue triangle about its x6, I get this. All right, so I want to expand on the powers of x6, and I want to show you guys something, the next step here. So let's do this. I'm no longer going to make the blue triangle rotate about its symmedian point. I'm going to make it rotate about some other triangle center. For example, let's make it rotate about, and to do this, I have to disconnect these two guys. Let's make it rotate about its in-center. So now I have a blue triangle family. I've elected the in-center of this triangle here to be stationary, and I'm going to make the blue family rotate about its stationary in-center. And obviously when we do this, I can show the loci of the three vertices. They are circles centered on concentric circles centered on the fixed in-center of the blue family. Now the first question you may ask yourself is, what's happening with the locus, or with the symmedian point of the red family thus obtained? Is it still stationary? You can see already visually by visual inspection that this red dot here is not stationary. What kind of curve is it sweeping? So let's go ahead and now light up the locus of this point here. I can light it up. There it is. There it is. It's this magenta curve. Okay. Now, numerically, this magenta curve, again, being swept by the symmedian of my inversive family, it is being reported up here as being an ellipse. So this simulator is actually internally equipped with an ellipse or a conic detector, and whenever a curve is numerically by least squares close enough to being an ellipse or a hyperbola or a parabola, I'll report it up here. So it's saying, look, the curve swept by this point x6 to the minus 1 is an ellipse, ELL. Here are the semi-axes of this ellipse, and here's the ratio of axes. Now what happens to this ellipse if I change anything? For example, if I change the radius of my inversion circle. Let's go ahead and do that. Okay, now you can see here that as I change the radius of my inversion circle, the inversive image is just getting scaled. So if you keep your eyes up here, you're going to notice that A and B are getting scaled accordingly, but the ratio, the aspect ratio of this ellipse is not changing. So it's just stuck at 0.66817. It actually jumped to its reciprocal because there's an issue here of what we call A or B, okay, and it might occasionally jump to the reciprocal of that, but you can see here visually that the ellipse is just remaining the same ellipse and there's no actual change going on here in its aspect ratio. Okay, so what we're seeing here is that the locus of the symmedian of the inversive triangle is a conic. It's an ellipse. What happens if I, instead of rotating about x1, I decide to rotate about x2, which is the barycenter of my blue triangle? So now let's go ahead and choose the barycenter here. Let's clean this up a little bit so we know what we're talking about. So yeah, so I have a triangle, and let's go ahead and change this triangle just for fun. Let's pick another triangle here, another random triangle, something like that, or maybe something more. Yeah, this one is even closer to being an isosceles, but you can see it's not an isosceles, but this one is actually an acute. So I'm going to make this acute triangle rotate about its barycenter, like so. What is the locus of its vertices? Let's go ahead and show that. There are these three concentric circles centered on x2, of course. And now let's look at the inversive image of this family. By the way, I don't know if I mentioned this on the other video or not, but inversions of circles with respect to some circle, for example this one, inversions of circles with respect to a circle are circles. So the loci of the three vertices of the red family are going to be circles. Let's go ahead and light them up. So here are the three orange loci of vertices of the red family. Okay. Now you can see here again that the symmedian of this family is not stationary. What is it sweeping? Let's go ahead and light it up. It's sweeping this magenta curve. It's also being reported to be a conic. It's an ellipse with these axes. Okay. If I change my inversion radius, the aspect ratio does not change. However, if I change the position of my inversion center, the aspect ratio does change. Okay. Now, is this the same aspect ratio as I was obtaining when I was pivoting about x1? Let's go back to x1. 0.64188 for x1, 0.59421 for x2. So no, the ellipses do change if you change the pivoting center of the blue family. Okay. Now let me show you guys a couple of phenomena here. There is a position for O that is going to make this ellipse become a degenerate ellipse, a segment. Okay, so I can make this ellipse become a segment by slightly nudging O to a particular position. Okay, I haven't studied what this position would have to be, but now the locus of I guess if O is on one of these ellipses, maybe this is the case, maybe, okay, I haven't studied this very much, but what you can see now is that the locus of the symmedian point is a segment. This is actually an ellipse that has collapsed to a segment. And likewise, so the minor axis is the length of the minor semi-axis is 0. Likewise, I can actually nudge O around to a position where this ellipse is going to become a circle. Yes, so you can see here the aspect ratio is pretty close to 1, and I can keep nudging this to the left until I get to 1. So now the locus of my symmedian is a circle. Why is it a circle? It's actually happening where the center of my inversion circle is the pivoting center itself. Okay, and I'm sure that there's an easy way to prove this one. Let's look at what happens when I'm pivoting about x1. So if I'm pivoting about x1, I also get a circle, but the geometry is not as obvious, right? So you can see here that the geometry, or maybe it is. Let me think about this for a second. Yeah, okay, so yes. So of course, if my center of inversion is the pivot point, okay, the family of inverted triangles, let's go ahead and scale this out a bit, is also going to be rotating rigidly about that center. Okay, So if that family is rotating rigidly about that center, it means that whatever that triangle center I choose is going to be describing a circle at this specific location. But what's remarkable about the Simedian point is that for wherever position of my inversion center, I get a conic, and also for whatever pivot that I choose for the blue triangle. So if I change this pivot to x2, as we just saw, I get a conic. If I change it to x3, the circumcenter, I get a conic. The orthocenter of the blue triangle, I get a conic. Let's watch that, and so forth and so on. Okay, so we're approaching the pivot. So let's do one more. x5, the center of Euler's circle. I also get a conic for the locus of x6. Let's move my center of rotation a little bit. You can see that that magenta curve remains a conic, okay, as I move my center of rotation a bit. And then we get to the case that we saw before, which is just a special case of all these cases we're looking at. If my center of rotation, or my pivoting center of the blue family, is the Simedian as well, you get a very degenerate case where the conic that is being swept by the Simedian of the inversive family is a point. It's a degenerate conic. It's just a point. This case is very interesting and very special. Let me just remind you that these blue concentric circles are the loci of the vertices of the blue family, and the orange three circles are their inversive images. There are three circles. If I move my O around a little bit, I can make these three circles become more visible. So we go back to topic on the previous video. Let me advance the pivot center now just to keep seeing that we get this nice conic rule. I'm going to make the pivot of the blue family now be the Jargon point. You can see here, if I scale this up, that x6 is moving along a conic. If I move my center of inversion a little bit, I can alter the shape of that conic. It's a small conic. If I now make my pivot be the Nagel point, now I'm moving the inversive Simedian is moving along this conic, which I can change by moving my inversion center, but it's still a conic everywhere, and so forth and so on. Okay, I'll get the same if I go to the Mittelpunkt, x9, for the pivot center, I get this magenta conic, x10, x11. So I've done this experiment all the way to x1000, and x6 will always move along a conic if, the Simedian of the inversive image of this pivoting triangle is always going to move along a conic. Can I make this conic be a hyperbola? I believe I can, but off the top of my head, I don't remember how I did that, but you can occasionally, and maybe this is not possible with x6, you can make this guy become a hyperbola. But right now we're only seeing ellipses. Let's just do this very quickly to see if I run into a hyperbola here. You can see as I advance, everything looks like an ellipse. So maybe there's something even stronger about x6. It's always an ellipse, okay? I have to check that. All right. Let's see, anything else I wanted to talk about? Okay, so I want to talk about one more thing in this video, and then I'm going to stop, which is, okay, so if I pick x6 for my center of rotation, and I observe what happens to the x6 of the inversive image, I see that it is stationary, as you can see here. What if I tried a different pair? Okay, I'm going to make this family rotate about x1, for example, the first triangle center in Kimberling's list, and I'm going to observe what happens to x1 of the inversive family. So let's do that. Let's go ahead and now say, okay, I want to rotate about x1, and so the blue triangle is going to be rotating about its in-center, and the red triangle is going to be its inversive image with respect to this green circle, and I'm going to watch what happens to the in-center over the family, and you can already see this heart-shaped curve sending us a lot of love. The locus of the in-center of the inversive is not anything simple. If I move the position of O, I'm going to change the topology of this curve greatly. You can see this if I do this. So I'm moving O to the right. The locus of the in-center is changing. It's becoming this compact curve here, and you can see that it changes its shape quite a bit. I'm getting a little bit of polygonal artifacts here. I can change that by changing the step with which I compute this locus. It's just going to make the simulation be slower. But you can see here that this is a complicated curve. Let's go back to the large step so that this thing animates faster. Okay, so what happens if I change perhaps, if I choose perhaps x2, the body center, as the pivot center, and I'm going to observe what happens symmetrically to the body center of the inversive image. So let's do that, and let's do that. Again, I don't get anything simple. I get this pink or this magenta curve for the locus of x2, even though x2 is one of the simplest, is a linear center, right? I mean, it's just the average of the blue vertices and the average of the red vertices, but even though I'm only computing the averages, this is not playing out nicely with the inversion of operation. So you can see that x2 now sweeps this very strange curve. If I move O around, I can change the shape of this curve. Now x2 of the inversive is undergoing two self-intersections. There are these two loops, okay, and so forth and so on. Now let's go to the final result, which is x3. Let's look at what happens if I pick. So let's clear this up. Let's start this thing again. So what am I going to do? I'm going to now pick the circumcenter as my pivoting center. So here I have a triangle. This triangle is acute because the circumcenter is in its interior, and I'm going to make this family rotate about its circumcenter. Okay, now let's go ahead and draw the locus of its vertices, three circles. Now something interesting happens here with the circumcenter, right? The locus of the three vertices of a triangle that gyrates about its circumcenter, they coincide. They are called the circumcircle. So this is a very degenerate family. And now let's go ahead and look at what happens to its inversive image. So let's go ahead and do that. And let's draw my inversion circle. And let me move this inversion circle a bit to the left. Okay. Now you get the same phenomenon you got with the symmedian. X3 of the inversive is collinear with O and X3 of the reference, and it is stationary. But I will argue that this is a more trivial result, because let's look at the loci of the three vertices of the inversive family. Okay, so they also coincide. Why do they coincide? Because the locus of each one of the vertices of my red family is a circle, which is the inversive image of the locus of each one of the vertices of the blue family. But the three vertices of the blue family have the same locus, the circumcircle. So the three vertices of my inversive image are also going to have the same locus, their circumcircle. And because the red family is inscribed in their circumcircle, in a fixed circumcircle, the circumcenter of the red family must be elementarily stationary. Okay, so this is a more elementary result, but it's very similar to the result where instead of actually making blue turn around x3, I make blue turn around its symmedian point. This one here doesn't have a simple direct explanation, barring some of you are coming up with some cool explanation for why this is happening. Okay, but although the two phenomena are very similar, so going back to x3, rotate about x3, look at the inversive image about x3. Now, the final thing here is what happens if instead of rotating about x3, I rotate about x1. So let's do that. I'm going to rotate about x1. Now, if I rotate a triangle about its x1, the locus of the three vertices are not going to be the same coinciding circle. They're going to be three separate circles. Likewise, the locus of the inversive vertices are going to be three separate circles. Let's look at what happens to the x3 of the inversive when we do this. It's moving. What is its locus? Oh, now it's a sideways. It's a sideways ellipse. Interesting. What happens if I now rotate about x2? Again, a sideways ellipse. If I rotate about x3, it's a point, as we just saw. If I go to x4, another sideways ellipse, and so forth and so on. So, like x6, the locus of the inversive circumcenter is always a conic. Now, this one I can say conic with more propriety, because I'm going to show you guys how this conic can be deformed into a hyperbola. And I can do this by simply moving the center of inversion. So right now I'm a hyperbola. Let's go ahead and scale this out. You can see here that the locus of the circumcenter of my inversive image is a conic, but it is a hyperbola. Does this hyperbola change if I change the radius of inversion? No. Basically just scaling its axes, but its aspect ratio shown over here remains the same. But you can go from hyperbola to ellipse by moving the position of my center of inversion. So I'm going to go through a parabola. This is probably close to a parabola, and then you become an ellipse. Okay, so there's a transition point, which seems to be happening exactly when O crosses this light blue circle here, which corresponds to the locus of the outer circle. So the outer vertex of the blue family. So if I make O cross that, then I switch over to a hyperbola. And I'm probably going to undergo some other transitions as I cross these two other circles. Now I'm back to an ellipse. Okay, and within this ellipse, there's going to be a circle if I'm right in the middle here. Of course, if O coincides with the center of rotation, and so forth and so on. So this is happening for the pivot center being x6. And if I make the pivot center be x7, I get another ellipse, and so forth and so on. So yeah, this is pretty nice as well. This is what happens when you're inverting with a pivot on the meeting point. Scale that up. So I guess this video showed a bunch of phenomena where we started in the previous video where the pivot center was the symmedian and the observed inversive center was also the symmedian. We got a point. We showed that the same thing happens here for x3. If you get x3 for the pivot point and x3 for the inversive, but that's a more trivial phenomenon. But I think the crux of the video here is to show that for whichever center of rotation you pick, the locus of either x3 inversive or x6 inversive are always conics. It looks like x6 is always an ellipse, and x3 can be either an ellipse, a parabola, or a hyperbola. Now, just to close, the center of rotation need not be a Kimberling center. It can be any point on the plane. So I can disconnect the choice of the center of rotation of the blue triangle from it being a triangle center by simply clicking here. And I can say, okay, hang on, before I do this, by simply clicking here, and now I'm going to call the center of rotation, the pivoting center, Z, and I'm just going to continuously move my blue family around and make Z. Z is an arbitrary point in the plane. It can be inside of a triangle or outside of a triangle. It doesn't matter. The locus of the inversive x3 continues to be a conic. So it is not a requirement that the pivoting center be a proper triangle center of the blue family. It can be any point on the plane, interior or exterior to my triangle. Let's repeat this when I'm observing not x3 but x6. Now I'm observing x6 of the red family. I'm getting a conic here. I can see I'm reporting the conic parameters up here. I can move my center of inversion, and that thing remains an ellipse. In this case, it doesn't look like that I can turn the x6 locus into a hyperbola. Its discriminant is always whatever it is. I think it's negative for it to be an ellipse. However, for the case of my of x3, going back to x3, this thing can be either an ellipse or a hyperbola. So I'm a hyperbola here. I'm going to move my Z around. My pivot center, you can see that I remain a hyperbola. It doesn't matter. I can change my my triangle. I can pick another triangle. I'm still a hyperbola, so forth and so on. So here's another family of triangles rotating about this point Z. Let's bring the Z a little bit closer to the triangle, maybe over here. Maybe over here. And now blue is rotating about some random Z on the plane. And you can see that with this particular choice of center of inversion, I get a hyperbolic path for x3. Let's move this away a little bit so My path becomes elliptic, and I'm just going to close with that. I'll see you on the next video. There's more to come. Thank you very much.